Circular motion. So before we can talk about circular motion, we need to go back and look at what net forces do. So we already said that a net force produces acceleration. Now, what does that mean? Well, remember that acceleration is a change in velocity, and velocity is a vector. So how could we change our velocity? We could speed up. What else could we do? Well, changing velocity isn't just going up, it could also be going down. So that could be slowing down. But remember that because velocity is a vector, if you change the direction you're moving in, you're also accelerating. So that could be change direction. So once again, a net force produces acceleration that makes you speed up, slow down, or change direction. Well, this change in direction, that's going to be our circular motion, or it could be going around a curve. Okay? So let's look for a second more specifically at speeding up. Speeding up occurs when the net force and the acceleration have the same direction as the velocity. So let's say we have a block here, and the total force on the system is to the right. Well, if the net force is to the right, the acceleration is to the right. If it's moving to the right and has a net force to the right, then we know that these two are in the same direction, and that's going to speed up. Slowing down occurs when they're in the opposite direction. So if the F net and A are opposite the velocity, you're going to slow down. So let's say V, the block is moving this way, but it has a net force this way. It will accelerate this direction, and when these two are opposite, it's going to slow down. So we already know that, but what happens to create circular motion? So for circular motion, we said that there's going to be a net force that's going to act to change the direction of the velocity. So when does that occur? So let's say this is a top-down view of a car driving around in a circle. So what direction is the car moving? If you think about the headlights of the car shine in the direction of the motion of the car. So the headlights shine straight ahead, so that's the direction of the velocity of the car. But the direction of the force is perpendicular to the velocity. So the net force is this way. Now, if the net force is to the right, then the acceleration has to be to the right. So when we have a net force producing an acceleration towards the center of a circle, the velocity is perpendicular to that net force and that acceleration. That is going to produce a change in direction. And that change in direction is going to give us this curve, specifically a circle. When the net force is perpendicular to the velocity, it has a name. If it's perpendicular to the velocity, it's acting towards the center of the circle. So we call this net force a centripetal force, but don't forget that it's still a net force. So that centripetal force, how can we remember that it acts to the center? The word center is almost written in centripetal force, is the center-seeking force. And the abbreviation is FC, and that C helps to remind us that it's towards the center. But again, I have to stress this, especially if you're doing more advanced physics, that centripetal force is a net force. And what does it produce? It produces acceleration, but not any old acceleration. We call this a centripetal acceleration. So what is centripetal acceleration? Well, regular acceleration, we said, was change in velocity over time, but there's an additional formula that's specific, and this specific formula is AC equals v squared over r. And the units, if you derive them, still comes out to meters per second squared. That's meters per second squared, all of that divided by meters gives you meters per second squared. So, what's the most important thing in this unit that you're going to get tested on? Well, the most common questions deal with what direction these three quantities are in. And centripetal force always acts to the center. And when we say acts to the center, it's acting to the center of the circle, or if it's part of a circle, then we would say the curve. Centripetal acceleration also always acts to the center. Now, why is that? It's because net forces produce acceleration in the same direction as the net force. So that's a net force, so it's going to produce acceleration in the same direction. And the velocity always acts tangent to the circle. So let's look at a circle here, and we'll do this as an example problem. And let's say that the ball is traveling around in a circle clockwise. So it's cruising around in this direction. And we're defining our directions of north, south, east, west off to the side here. And let's look at the directions that FC, AC, and V are going to act in. So the velocity is going to be tangent to the circle. So what is a tangent line? A tangent line, you know from math, is the line that is basically straight off the edge of that circle right there. So at this point, the velocity acting tangent to the circle is going to be that direction. And we know that the centripetal force must be acting perpendicular to that velocity. What's perpendicular to that velocity? That's the force that's acting to the center of the circle. And because this is a net force, it produces acceleration in the same direction. Now, it really doesn't matter whether you make this vector shorter or longer. I'm just making it shorter so that we can see it more easily. But the key idea is that they're acting in the same direction. So what direction is velocity acting? It's acting to the east. What direction is centripetal force and centripetal acceleration acting? To the south. Now, this does seem sort of tricky or non-intuitive, that something's moving this way, but being pushed to the center of the circle, yet it's not getting closer to the center of the circle. But think of it this way. If there was no centripetal force, what would the ball do? The ball would move in a straight line. That is Newton's first law. So if there was no centripetal force, the ball would move out to a position here. Well, what did that centripetal force do? It moved the ball towards the center of the circle to here. So in actuality, the ball was moved to the center of the circle. It's just moving it from where it would have gone if there was no centripetal force. We know that F net equals ma. But what happens if we say that this is centripetal acceleration? Well, what causes centripetal acceleration? Centripetal force. So our formula is Fc equals mac. So they give us this formula, Fc equals mac, but we also know that AC is v squared over r. So we can substitute in v squared over r into AC. So if we do that, we have AC equals v squared over r, and we take this and substitute that in, then we can say Fc equals mv squared over r. So this formula is not given on the reference table, but it is a way to solve for the centripetal force. So let's go ahead and solve a problem. Let's say we have a car that's traveling around in a circle counterclockwise. So that's going to be this direction right here. And we're given the car mass, the speed, and the radius. Now, remember that when we're talking about the velocity, we have to include the direction. But the speed is referring to how fast the car is moving at any point in the circle. So the speed means we don't have to take into account the direction. The radius of the circle is obviously from the car to the center. So the first question is, find the centripetal acceleration and the centripetal force. So we know that centripetal acceleration is v squared over r. So we can just put in the numbers. We have 20 meters per second over 180 meters. So that's going to give us a centripetal acceleration of 2.2 meters per second squared. To find the centripetal force, we could do Fc equals mv squared over r, but we don't need it because we already have AC. So we can just put in 1,200 kilograms times 2.2 meters per second squared, and that gives us a centripetal force of 2,640 newtons. Remember, these are vectors, so we need to include direction. It says label velocity Fc, V, Fc, and AC. So what's the direction of these velocity, centripetal force, and centripetal acceleration? Well, if it's moving in this direction around the circle, what is tangent to the circle? Well, our tangent line looks like that. So our velocity is going to be south. What direction is the centripetal force? Remember, centripetal force always acts to the center of the circle. So that's going to be our Fc. And our centripetal acceleration always acts to the center of the circle. So that's going to be the direction of AC. So Fc and AC are to the east. The last question says, if there was ice, so let's say this car is going around this circle and friction is what is driving the car around the circle, and the car hits a patch of ice, there's going to be no friction to push it to the center. So therefore, what direction is it going to move? Straight. And the car is going to go off of the curve and land at point B. So this is getting into slightly more difficult physics for centripetal force, but we need to understand this to be able to solve problems like derivations and questions where we actually have to take the centripetal force and substitute in a new force. So let's say we have a car driving around this curve like this. We would say that the centripetal force is acting to the center of this curve. But what is the centripetal force? Remember, it's a net force, so something needs to be causing it. Well, what's pushing the car around the corner? If there was no friction, the car would travel off in a straight line. So the net force, the centripetal force, Fc, in this case, is FF. So if we were to write a net force equation, we would write F net equals Ma equals FF. But because it's a centripetal force, we can say Fc equals Mac equals FF. What would it be if it was the Earth going around the Sun? Again, we have a centripetal force that acts to the center of the circle. But what is that force? It's the force of gravity. So we would write our net force equation, F net equals Ma equals Fg. But in this case, F net is a centripetal force, so we can say Mac. And what is the force of gravitation between these? Well, we could put in G m1 m2 over r squared. And finally, if we have a roller coaster, and let's say this roller coaster is going around in a loop, the centripetal force is acted towards the center of the circle. Now, if the car, the little roller coaster cart, is going fast enough that gravity is not enough to push down on it, the track is also going to push down. So we have two forces that are acting as the centripetal force, and that would be the force normal of the track, and the force of gravity. So our net force equation would be F net equals MA equals Fn down plus Fg down. What can we do to solve it for centripetal? Well, we would just change that net force to Fc and MAC.